So we left off, I was starting to talk about the process of actually conducting magnetic particle, and then we did a demo in class. So I'm just going to kind of go through these. We went through them somewhat quickly, but we're going to look at the reasons for why we do some of the steps that take place during inspection and why it's run the way it is. So this is where we left off, where we were talking about using the coil. Just a quick reminder that we need to check magnetic fields. We have a magnetometer or a flux gauge. Okay, it reads in Gauss. Our test bench itself, which you've all seen at this point. And then when we're talking about the coil, just a reminder that it's going to magnetize properly, approximately 6 to 9 inches each side. So if we're working with a longer part, a long crankshaft, for instance, you're often going to need to use the coil at kind of one end, magnetize one end, and then slide the coil down to do the opposite end. Okay, or maybe even 3 places if it's a particularly long part, like a landing gear, strut leg, or something of that nature. Okay. So when we're using this, remember the current and the magnetic field are going to be 90 degrees to one another. So using the coil, current flow is going to be around the part, as shown by the dashed arrows. That's going to cause a magnetic field to align left to right or longitudinally along the part. Okay, and what they're showing here, the magnetic lines of force. Now, what's not shown here is that the magnetic lines, if you've seen like a magnet with iron particles around it, you get the magnetic field jumping from one end to the other. So on this part, one end's going to be the North Pole, one end's going to be the South Pole. Oops, go back. Doesn't want to click for some reason. There we go. One end's going to be the North Pole, one's going to be the South Pole. And so what's going to happen is in addition to the magnetic field in the part itself, there's going to be a magnetic field that leaves the part and kind of jumps through around the outside, right? They create a field that surrounds the part. So that field's in the part and outside the part. When we do our magnetometer check or we run our Gauss gauge over it, we're picking up that field on the outside of the part. When we're applying particles, it is sticking to the field that is essentially in the part, but that is going to kind of jump any kind of a crack or a gap. That's where it leaves, anywhere it leaves. So when we do a longitudinal field using the coil, we're going to get a very, very strong indication with our Gauss gauge when we check it. Typically 10 Gauss or greater. We'll often peg out those Gauss gauges max out at 10. They're going to be pegged out. It usually goes off the scale, especially larger parts. And that's because you get that field has to jump from one end to the other. You create a flux line outside the part going from one end to the other. And so there's a lot of magnetic force on the outside, okay? But what that means is those magnetic lines of force, now it's working, there we go, maybe. Those magnetic lines of force, areas like if we're looking for what's called a transverse defect that is perpendicular to the magnetic lines, we're going to get a good indication because that field that's traveling left to right is going to have to jump over this crack. We also will probably get a pretty decent indication on something that's at an angle to it, like this 45, shown just left of that. But a crack that's longitudinal, that's running the same direction as the lines of force, the field will not have to necessarily jump from one side of that crack to the other. And so you'll get a less obvious indication, or maybe no indication at all. And we saw that during the demo. Remember with the part, I had those steel parts with the crack, and it was in this direction, right? And when I first magnetized, I used the head and tail stock first, which we'll talk about in a minute. It was a lighter line, it was a fainter line. And then when I used the coil, it got brighter. There was a stronger indication there. And so that's why we'll do this in 2 different directions. That's why we use the coil and the head and tail stock to make sure that we don't miss a crack like this. If we only use the coil in this case, there's a potential we could miss this longitudinal defect because it may not even grab If it's perfectly aligned, a very straight line, it may not grab any kind of particles at all because there's really no field jumping from one side to the other. Okay? So that was using the coil like this. Okay? When we use the head and tail stock now we're going to, instead of running current through, and the coil, by the way, this is just a big coil of copper wire in here, okay? When we use the head and tail stock, the current in that case doesn't run through it. When we use the head and tail stock now, the current's going to actually run through the part, and it creates a circular field around the part. So it looks something like this. So now our current is running through the part itself. Our magnetic field is essentially going to be little rings that surround the part. And because of that, because the essentially one side and the other is north and south pole, like the top and the bottom is north and south pole, because the field doesn't have to jump from one end to the other, when we go to check it with our Gauss meter, we're going to get a much lower reading. Typically it's somewhere around anywhere from 1 to maybe 4 Gauss, okay? Is about the strongest you get. And that's okay. It's because of the nature of that field, it doesn't need to jump from one end of the part to the other. And so what we're going to see here is now that longitudinal crack, that crack that runs left to right, this is going to show up really well because it's perpendicular to the magnetic field. We should still see that 45-degree crack. Irregular cracks, most cracks aren't going to be nice and straight longitudinally or nice and straight, transverse. They're going to have some kind of shape to them. They'll may show one, in this case, this irregular crack that kind of runs left to right. This one's going to show up probably better than the one that's more transverse oriented, but they probably will both show up to some extent. And then again, that in this case now that transverse crack may show up, but likely it's possible it won't even show up at all. And so again, that illustrates why we need to do the magnetic field in 2 different directions to make sure we don't miss something that's parallel to one field direction or the other. Okay? The last thing is if we have a circular part, or it can even be a hollow square part, is we use a center conductor. So here is a part. This looks like, to me, it looks like it's out of a landing gear. It's kind of the lower cuff area. It supports the inner leg inside the outer leg. On a copper rod or a bronze rod. And when we do this, we're going to run, so things like rings, ring gears, rings, tubes. It can even be square tubing. In theory, we could test that square tubing as an example with a center conductor. It really isn't there's no real advantage to it in that case. But circular parts are hard to clamp into the head and tail stock properly. Right? They aren't going to get you're not going to get a nice, strong, especially to run current through the part. It's going to be really hard to get those pads to get good contact on each side and not run the risk of having a poor contact area that could cause heat to build up and even potentially cause spattering and welding, melt the metal because it's such a small contact area. So we use a non-ferromagnetic conductor. These can be copper, brass, bronze. In theory, they can be aluminum. You usually, though, see bronze like what we have. Bronze rod, they're the strongest of these items. Brass is very soft, as is copper. And so when you're clamping it in there, you want to, if you're clamping it in there, it is going to build up some heat. So if you use a very soft material, there's a potential for it to soften and bend. In fact, one of our bronze rods got overheated. I've got it on the shelf. You can see it kind of bent in there. And that's because that head and tail stock were pushing on it. It got hot, and as it heated up, it sagged and kind of got bent. But the current flows through the conductor. It creates a circular magnetic field around the conductor. Now remember, these are not magnetic. They're not going to hold on to a magnetic field. Bronze will not. It's not going to retain that magnetism. It has very low retentivity. But when the current is actually flowing, there will be a magnetic field. Just like a copper wire, you get a magnetic field around the outside of a copper wire. This is just a much stronger. This is a copper wire running upwards of 2,000 amps through it. Okay? And that field is going to intersect the part that's hanging on that rod or around the outside of the rod. And that is going to cause a magnetic field. That's going to induce a magnetic field in the steel part or the ferromagnetic part that you have surrounding the rod. And so the rule of thumb here is it magnetizes around the circumference or 4 times the diameter. And I described this during our demo, but I didn't really draw it. So what we have is if we have a copper rod, okay, and then we have some kind of a part hanging around the outside of it. I'll just say it's a ring. I'm not going to draw a bunch of teeth. We're going to get a magnetic field. The magnetic field that's going to form around this copper rod is going to be somewhere around 4 times the diameter of the conductor. Okay? So our diameter here, right, D, we're going to get twice the diameter here, so D, and then a second diameter, right? And we're going to get twice the diameter going this direction. Okay? So that's where our 4 times the diameter. So we are effectively, in this case, we would effectively magnetize this area right here. Okay? Now, we will still get some magnetic field down here. It's just, it may not reach that saturation point, right? Because we've got we want to get that saturation point so we get the strongest magnetic field possible. So we get the highest likelihood that we'll see an indication. Okay? So in order to get the rest of this part to be magnetized, we're going to have to turn our conductor. So here's what it looks like when we're hanging that rod in there. Okay? And so you can see here we have a fairly skinny rod, a fairly large gear. In this case, we would have to rotate it several times. Okay? We'll get to, I'll do the calculation here in a second. What's happening looks like this. The magnetic field is, you can see it's the magnetic field that forms around this bar, it's going to be kind of parallel in some areas, perpendicular in other areas. So it's going to have different kind of orientations. So it'll show both transverse, and then along the top, it'll show cracks running kind of both directions. So here's what I just drew. And the other thing to point out here is 4 times the diameter, it'll actually magnetize a little bit more on the inside than the outside. Because see, it goes from kind of the edge of the part. So it'll be 1, 2, and kind of 1, 2. So on the inside of the part, it'll actually magnetize a little bit closer to the middle than the outside of the part. But we've got to deal with the outside of the part. We're dealing with the outside diameter because we want to make sure the entire part gets magnetized properly. Okay? So in order to get that, we have to figure out what the circumference of the part is. And we have to divide the circumference of the part. We divide it by 4 times the diameter of our rod. Okay? And then we have to round up in order to decide. So if that comes out as anything besides the whole number, so say it's, in this case, we go here, this one's roughly, 3 times, right? We would have to rotate this at least 3 times. If it was 2.9, we would still have to rotate it 3 times. Okay? Even if it's 2.1, we would have to rotate it to 3 different directions. We would have to rotate it, in this case, 120 degrees. Right? So I usually have people do kind of an exercise, figure it out. How many times do we rotate? Okay. So that's everything we do on our bench. So what are the 3 methods we use our bench. Just a quick review. What are the 3 ways we can magnetize a part? 3 directions. How do we do it? What do we use? What's the first one? Longitudinal what? Field or current? Longitudinal field. What do we use to create a longitudinal field? That's the coil. We're going along the length of the part. Okay? What's our second way? Circular magnetic field. How do we create a circular magnetic field? Current through the part using what? The head and tail stock. Okay? And our third way of magnetizing a part, typically a circular or hollow part. What's that called? What do we use? It's a center conductor, okay? It's a non-ferrous, non-magnetic center conductor, okay? So those are the 3 ways we do it on the bench, and we're able to do our part. Now, we can't always fit a part on our bench. Sometimes it's too large. Sometimes it's still connected to an airplane, okay? And in that case, we have portable equipment that can do it. We use something called a yoke or prods, and these provide a method of magnetization without being there. The other thing we'll do then is typically we can't dump a liquid all over something that's out in the middle of the hangar. And so we'll use particles that are either in like a dry powder, it's almost a dust form, very, very fine metal powder. Or we'll use aerosol. So it's an aerosol propellant can that's basically shooting out that same dust. It's just suspended in an aerosol medium. And this can be visual or fluorescent. So it can be different colors, visible light colors, typically things like red. If you're doing a dark steel part, it's like a light gray oftentimes, or even like a yellow. And then fluorescent. Fluorescent is typically a bright yellow or green. And what would we use with fluorescent in order to view that properly? We're using a what? A black light, which is ultraviolet. It's right on the edge of the ultraviolet spectrum. So this person here, this is using a set of what are called prods. And so essentially, this is a big power supply. It's almost like a welder, that is running to these copper rods that are inducing a current through that part right there. We're sending a current through the part. Okay, so prods send a current through the part. And that current running through the part is going to create a magnetic field in the part. And then what he has in his right hand here is a little, it's a little puffer or blower type item. Has anyone ever done like camera lenses, everyone seen those little puffers you use to like clean a camera lens? It's like a little puffer ball with a brush on the end. Think about that without the brush, and then you put some stuff in it. So he'll turn on current, and he'll puff the powdered stuff on there, the powdered indication material. A yoke looks something like this. These can be used 2 ways. Now a yoke is not sending current through the part. That's the big difference between the 2. So prods actually send current through the part. They're almost like using a head and tail stock. Okay? A yoke is a big electromagnet. Okay? These don't send current through the ends. What they do, when this thing gets turned on, one end becomes the North Pole, one end becomes the South Pole. It creates a very strong magnetic field between, the 2 ends of the yoke. Okay? Prods run current through. A yoke creates a strong magnetic field. See, it's just saying magnetic flux here in the legs. It's not actually sending current through. The current is up in the handle. There is a coil of wire that surrounds an iron core that attaches to those legs. Okay, it's a big electromagnet. These are probably what I saw most common when we did field. And honestly, we didn't do a lot of mag particle on the airplane, but these were great for another use. These are AC. So it shows a north and a south pole. That's going to swap 120 times a second, or 60 times a second, in the United States. It's 60 hertz, right? We're just taking current, running it around a coil, creating a big electromagnet. Since we have AC power here, it's going to be an alternating magnet as well. Most of the time, you press a button on it, press and hold, magnet comes on. As soon as you release the button, magnet shuts off. But if you're dealing with a steel part, it's going to leave a magnetic field behind. And you can see here that magnetic field in the part will create a crack, and we can spray either a powder type indicator or an aerosol type indicator on the surface of the part, where it's going to be drawn to that, where that flux is jumping across that crack. Okay. These were also used for another thing. What can we do with a magnetic field if we remove a magnetic field? What do we have to do with our parts when we're done inspecting them? Demagnetize. We use these quite often when our aircraft had a lightning strike. When aircraft get hit by lightning, that current that runs through the airplane can actually magnetize parts on the aircraft. Steel parts on the aircraft, things like the landing gear legs, all the screws, all the steel screws that hold panels on. The windshield frames can get magnetized. And so what we would do is, as part of a lightning strike inspection, we'd have to go around with Gauss gauges and see if we found anything that had residual magnetism. And if we did, we would take one of these yokes, like for the landing gear, we'd put the legs, if we had the landing gear, if my bottle was like a landing gear, we'd bend the legs on each side, you'd press and hold the trigger, and you'd pull the yoke away. And that would demagnetize the landing gear leg. And you would do that a few times here. You might have to do it a second direction. And we would go through and demagnetize it so that it wouldn't cause interference with our navigation systems. It's particularly important on aircraft that have what are called AHRS systems, attitude heading reference systems. They use magnetic flux sensors in the wings to pick up the Earth's magnetic field to run the navigation system. Now, you don't want to demagnetize the screws right by the flux sensor. Okay? This will fry a flux sensor. But if you turn it on up on the windshield, you'll see the whiskey compass spinning around inside the airplane. Okay? So you can use them to demagnetize as well. As you turn them on, pull it away, shut it off, turn it on, pull it away, shut it off, and you'll demagnetize parts on the aircraft. Here's how those prods work. So the prods running a current, they actually create kind of two circular fields. So you can see the yoke creates one field running between the two legs of the yoke, whereas the prods create two circular type fields in the part. Okay. And you can see by moving them around, they're showing a weld inspection, for instance. By moving it around, you can get, you might move them to different areas so that you can see if this part was hitting, if the far left part of either field or the far right part of either field was hitting that crack, it would be parallel to the crack, so you probably wouldn't pick it up very well. But you can see here where it's kind of in between the two prods, that field is more perpendicular to the crack, and so it'll show up really well. So you might have to move the prods around. Same thing with the yoke. You have to move the yoke around, and you often move the yoke 90 degrees. You do a check one direction, you do a check the other direction. And that way your magnetic field is going two different directions. Yeah. Correct. Yeah, this is all for ferrous materials. Yep. Magnetic particle inspection is for ferrous materials only, even when you're using yokes or that kind of thing. So our method that we're doing, what was demonstrated in lab, is called the wet continuous method. And this is the standard for aerospace for parts that are being typically done in a back shop where you have a bench available. Okay. As I said, there may be some where you do it out on the aircraft using prods or yokes. In that case, you're almost always going to use a fluorescent particles in an aerosol type can. We really don't use dry powder very much in aerospace. But wet continuous, what we're doing on the bench is we have our suspension material is a light oil. That liquid that you saw in the bench is basically like a very thin mineral spirits. And we have to apply it while current is being run through the part or around the part. But we don't want to continue to apply it when we shut the current off. So that's where you start wetting the part. You hit the button on the machine to turn the current on, whether it's running through the part or through the coil. You stop wetting the part and then you release the button. Okay? The reason you stop wetting the part before you release the button is you could, that flow of fluid can, in theory, wash the particles away, if as the magnetic field is reduced a little bit when the current stops running. So continuous wet residual exists. We're not doing that. We're doing wet. Continuous is we're applying it while it's on. Continuous wet residual is where you magnetize the part and then you apply the fluid. Okay, there are some cases where that's used. We're not doing that. That's called residual versus wet continuous. Okay. Dry in portable, or more common is dry is aerosol in the portable form. We actually have aerosol if anyone wants to try it. I don't have a set of yokes, or I don't have a set of prods. But if you want to use the bench when you do your self-design to magnetize a part, and try using aerosol spray instead of the liquid, I do have cans of aerosol, and you can use the bench. You can run aerosol, you can run dry powder on the bench. But you just don't want to mix a bunch of that dry powder down into, it's not the same powder that's mixed into our oil bath. Wet continuous, they're magnetizing the part while they're putting it on. You saw that. There's the puffer ball. Okay. So you can see the particles here kind of forming lines, and those are parallel to the magnetic field going between the two legs of the yoke right here. Various colors of ferromagnetic particles. They said red, different grays and blues, kind of a yellow color, burnt sienna. I don't know, what are your, think back to your crayon box in elementary school, right? Or go look in a nail polish aisle. They've got some real creative names there, I've discovered. 2 daughters, growing up with a brother, and now I've got 2 daughters. It's been eye-opening. Here is, these bottles up here show 14A and 20B. This is what we're using with our wet system. So the bench is filled with a carrier solution, and then I'm mixing, then we're mixing dry particles in there, and they are in a suspension. Okay, they're not dissolving in the bath. When we add the dry powder to the bath, it's suspended. The particles are still the particles. We just use that pump. We use a pump on the bath to keep them circulating and stirred up. Okay, when that's off, if you go look in there right now, without turning the pump on, if you pull those grids up that make up the test bench, and you look down, it'll be clear fluid with all the particles will just be settled at the bottom. That tank underneath has a V trough in it. So they all settle into the V at the bottom center of the trough. And then the aerosol cans look just like any other aerosol can.